And now let me introduce our first speaker, Dorit Aharonov from the Hebrew University. Dorit is a Weizmann alumna, right? From Masters? No, like she went here? Okay, Weizmann flank out. So Dorit is very well known in quantum computing in part for her contributions to Hamiltonian complexity and quantum fault tolerance. For me, it's sort of a special honor to introduce Dorit because I got to know the area by taking her class. So it was already over 20 years ago. So whatever credit or discredit for my being here, some of it should go to Dorit. And I'm personally very happy to have her here. So Dorit is going to tell us about this exciting work on testing quantum advantage. Dorit, please.
Great. Thank you. Can you hear me? Yeah. Thanks, Vika. And thanks a lot for organizing this event. It's been really called for. I was just my own fault, but I realized that my talk should be half the length that it was supposed to be right now, 5 minutes ago. So we'll see how it goes. There are 5 minutes at the end that I really want to say. So whenever, Zvika will tell me, and at that point, no matter where I am, I'll just jump to these 5 minutes, and then we'll hopefully have a few minutes for discussion. Okay, so what I want to tell you about is this question of testing quantum advantage. Basically, computational power of physical systems. Physical systems are all basically relying on the same type of elementary steps, local, simple updates. And the extended Church-Turing thesis, stated by Bernstein-Vazirani from 93, says that no matter what kind of classical computation you're using, it's basically under very mild restrictions, it's basically going to be the same, up to polynomial overheads of simulating. So all physically realizable computational models can be simulated polynomial time by a probabilistic Turing machine. Okay, enter quantum computation. And quantum computation basically is the only candidate that we know today that seems to violate this thesis or promises to violate this thesis. And basically, it's widely believed that it violates the thesis for two reasons. One is a mathematical conjecture that BQP, bounded quantum polynomial time, the class of problems that theoretically can be solved in polynomial time by the model of quantum computers, is strictly larger than BPP, bounded polynomial, probabilistic polynomial time. So classical tractable computations. So this is a mathematical conjecture. And I think it's very safe to say that this is extremely widely believed, this conjecture. The other reason for believing that quantum computation violates the extended Church-Turing thesis is that quantum systems can, in principle, physically implement BQP, quantum circuits. And that, I think, is less widely believed, though very widely believed also. And together, these two basically imply that quantum computation violates the extended Church-Turing thesis. Okay, one of the supporting evidence for two is a theoretical construction of fault-tolerant quantum computation, which basically says that as long as the noise is local, independent or with slight dependencies between the different parts of the system, and below a certain error rate, constant error rate, one can simulate using noisy quantum devices, ideal quantum devices with only polylogarithmic overheads. Okay, great. So for that reason, we believe that quantum computation violates the extended Church-Turing thesis. Okay, and this is an extremely important belief underlying the field of quantum computation. Okay, I mean, this is why we're trying to build quantum computers. It's because we think that there would be exponential overheads by applying computations using those computers. And it also is believed that all these different physical systems basically are capable of providing this universal quantum behavior if controlled well enough. Okay, and one of the ways to view this is that basically there's a phase transition. between quantum global behavior and classical global behavior. First, if the error rate is small enough, you'll have the ability to perform quantum behavior in large scales. And once the noise rate is above some value, this ability disappears. Okay? And below that value, it's sort of almost a different phase of matter. It's actually a phase of matter where you can actually perform exponentially faster quantum or universal quantum computation or universal quantum evolution. Okay. Okay. I'll skip this comment. Okay. So, given the importance of this assumption, it's worth asking, what is the evidence that we have for the fact that for our belief that quantum computation is indeed going to violate the extended Church-Turing thesis? And I should say that that I owe my own doubt about this to Oded Goldreich and to Madhu Sudan in a very exciting discussion I had with them in 2004. I was sure that, of course, we have evidence for that, and Oded and Madhu separately argued very vigorously against that. And it was at Radcliffe Institute, and I was sort of running to the physics department and saying, just give me your evidence, and I'll just show them that evidence. How do you go back? This. Well, I didn't find an evidence, and I think that it seems very hard to give evidence from current experimental data. Okay, so this is the topic of my talk. Okay, so I'll first mention maybe 1 minute about quantum simulations, and then I'll mainly devote most of the time to quantum supremacy. And this is the 5 minutes I really want us to talk at the end. Okay, so just a remark about quantum simulations. Quantum simulations was the motivation of Feynman for inventing or for thinking about quantum computers. And basically, one can ask whether quantum simulations, or even just the ability of physical systems to evolve as they do, is not evidence for a quantum advantage. I mean, it's hard to simulate quantum systems, and therefore maybe we already have evidence of quantum advantage given the fact that quantum systems run as they do. Okay, so this is something that is very questionable. I forgot to say that when Madhu Sudan and Oded Goldreich convinced me of the lack of this evidence, or maybe raised the doubts about the lack of this evidence, basically what came out of this discussion for me was the desire for, the need for a challenge. And the challenge is really something that consists of 3 sort of wavy requirements. First of all, a problem that's conjectured to be super polynomially hard for classical computers. Secondly, one whose solution can be verified. And thirdly, that there is good evidence that quantum computers can solve it for large instances. Okay? Okay, so going back to the simulations, the thing that's missing in those simulations is really that we don't have a definition of the first requirement. We don't have a definition of a hard problem. A hard problem with an input and an output, which we really think that the system solves, and which we think that classical computers cannot solve. And I challenge you to actually come up with such a problem. This is really a very, very important problem to come up with this. Okay, and I don't know of such a problem. And I should say that quantum simulations is a very important field and a very promising direction in which quantum advantage is people attempt to provide quantum advantage within this realm. We know that Hamiltonians, that there are universal Hamiltonians for simulating general quantum Hamiltonians. So quantum simulation is it has a theoretical foundation that, just like quantum circuits, you can use quantum Hamiltonians to simulate a generic quantum evolution. with only polynomial overhead. And in a recent survey, indeed, it was argued that using such quantum simulations of certain Hamiltonians by other Hamiltonians, we can see practical quantum advantages. But this is a reason, this is an indication for the confusion, the very strong confusion about the notion of quantum advantage. If we really look at what they mean by this quantum advantage, they actually mean that they can simulate physical systems that they don't know how to simulate otherwise. They simulate that by quantum computers, but there's no answer to the first challenge in this wanted 3 requirements. In particular, there's no problem that they can pinpoint that is conjectured to be hard. Okay. So there is a reason for the hardness of finding such a problem. And one reason is there is this inherent difficulty in actually verifying quantum evolutions. And okay, so if you look at an experiment, the standard experiment, it consists of 2 things: a classical, the experimental setup running the experiment, and the theoreticians predicting the outcome of this experiment. And for a classical theory that you want to verify, this is easy. You just predict the outcome and compare to the outcome of the experiment. But in the quantum setting, this is impossible to do. The left-hand side we cannot do exactly at the place where we want to verify, exactly at the for problems or for evolutions which we think are hard to simulate. We don't know how to actually make the predictions because they are hard to simulate. So what is it that we're going to compare to the outcome of the experiment? Okay, so this side, if we are trying to test many-body quantum systems, this side is impossible, at least in polynomial time. Okay. Okay, so in the predict and compare paradigm, we cannot efficiently test the high complexity regime of quantum mechanics. And this has been a source for a lot of work in the past decade or more, including basically all the organizers of this day. And it has been resolved to a certain extent, meaning we now know, using interactive protocols, how to verify even evolutions in quantum mechanics that are extremely hard to predict. In fact, universal evolutions, both if we just exchange single qubits and we trust the quantum mechanics for single qubits, or using only classical interactions if we under computational assumptions. So the efficient verification problem was solved, but using those constructions, nobody actually tested a problem that stands the 3 requirements, in particular, that stands the requirement that it is hard to simulate it is hard to solve by it is conjectured to be hard by classical computers. Okay, so good. However, this issue of verification might not be the main issue. Okay, so it might be that we don't actually need to go to this problem, to the question of how easy or hard it is to verify. It might be that it is enough for us to restrict ourselves to small instances, small being something like 50 qubits, or maybe even 30 qubits or 20 qubits, and convince ourselves that up to this number, we can actually solve, using quantum computers, problems much faster than classical computers. And maybe the verification could take us exponentially long. This is we'll still be satisfied with that, I think, if 20 or 30 is considered something that is large enough. So maybe you can give up the efficient verification and require just verifiable. Notice that in my 3 requirements, I didn't write efficiently verified, just verifiable. So let's go to this exponential classical verification. And let's seek for problems where we can actually show quantum advantage in this setting. Now, I want to say that quantum advantage I'm using here with caution, because of this issue of a very, very long list of different ways to interpret these terms. So I basically mean violation of the extended Church-Turing thesis. Okay, so asymptotic quantum advantage. So now the question is, can we actually, even if we give up the efficiency of the verification, yeah.
But how can you test like an asymptotic advantage, right? I mean, this is the only thing that you cannot actually like really experimentally test, right? Because any experiment has just a finite size.
Yeah. Why are you doing quantum computation?
To solve actual problems that people care about, maybe?
But why do people care about that? They care about this because, because of a finite statement about an infinite asymptotic situation. There's no, we can talk about this for a long, long time and we won't reach a conclusion, not because it's an extremely important problem, but basically the problem goes back to all of theoretical computer science. Why do we believe that something is polynomial versus exponential, even though we are dealing with finite systems? So we are actually, I mean, part of the belief underlying theoretical computer science and quantum computation as part of it is really that we see the asymptotics at finite cases. So this is why I basically wrote these three requirements of, these three requirements. There's good evidence that quantum computers can solve it for large instances. It's not a theorem. It's the interplay between physics and computer science, and there's no hope for a theorem. Okay, so okay, so back to this question. We are looking for such evidence, and we're looking for that in the context of NISQ. I'll explain what NISQ is in the last 5 minutes of my talk, but for now, I'm just referring to NISQ as quantum computers without error correction. Okay. So noisy, very noisy quantum devices, noisy intermediate scale quantum devices, and this is what we have right now, other than physical systems that we can control in the lab, not part of quantum computers. And we want to show this exponential advantage or this violation of the extended Church-Turing thesis in this context. Okay, so we can ask, do we even expect scalable violation of the extended Church-Turing thesis in such NISQ devices? I'll leave this question to the last 5 minutes. Okay, so now what did people actually try to do in this context? Well, in the past 10 years or so, basically there was the most effort in this attempt to find quantum algorithmic advantage came in the form of in the context of random circuit sampling. So I'm sure, I mean, everybody in the audience heard about Google's claim of quantum breakthrough, quantum supremacy or quantum advantage, where they basically use random circuit sampling, which means pick up a random quantum circuit according to some distribution and run some tests on its measure it, run some test on its output, and then compare that the computation within that test. For example, linear cross-entropy benchmarking. I'm not going to define it here. To what classical computers can do. Okay, so use current noisy intermediate scale quantum devices to sample from random quantum circuits, and use some statistical tests to evaluate how good the device is performing, and claim that the same performance cannot be achieved classically. Now, okay, so these tests, not only Google, but also the university UCST from China, also demonstrated such advantages or such experiments on 53 to 60 qubits. And these are really extremely impressive experiments. And there are claims about their advantage over classical algorithms in finite cases. And I'm not going to say anything about those finite cases. Okay, I'm just talking here about the attempt to gather evidence for some violation of the extended Church-Turing thesis, which is an asymptotic statement. Okay, so this means that I'm actually interested in problems which are thought to be polynomially solvable by quantum computers and exponentially or super polynomially solved only by classical computers. Okay, so this is the problem, random circuit sampling. You have a random circuit, and I'll use the error model in which there's probabilistic noise on each qubit with some probability that qubit becomes completely mixed between every layer in the circuit. And the circuit is chosen randomly. And for now, let's just think of each unitary gate chosen from the Haar measure, a random unitary gate. And then sample a random circuit with some depth d. The depth d is important. Fix the circuit, obtain m samples from the same circuit. And this will be sampled from the noisy distribution. So if the actual distribution is p tilde will be the noisy distribution. And then perform some statistical test on it. It might take exponentially long to perform this test as a classical computation. And then maybe repeat the procedure for several times. So that's the RCS framework. Okay, and the theorem that we proved recently is that basically there's a classical algorithm that can fool any such experiment. So there's a classical algorithm that on input a random circuit C on n qubits outputs a sample from a distribution that is epsilon close in total variation distance to the noisy output distribution p tilde that comes out of the circuit with success probability at least 99% on the choice of the circuit. Okay, so you first pick a circuit, and for most circuits, we'll be able to simulate the output distribution for that circuit to within some total variation distance. And the time it will take, this is crucial, is polynomial in n and in 1 over the epsilon. Okay, so we have m samples, and our algorithm is going to generate those competing m samples in time, which is polynomial in the number of samples and in n, such that no statistical test can tell the difference. And the point is that if we only, it's a very simple fact that if you only have m samples, then if you require epsilon to be 1 over m, there's no way we can information theoretically distinguish between the samples. So if each of the samples is drawn from a distribution which is 1 over m close to the right distribution, m samples just do not have enough information to distinguish between the two situations with good enough confidence. So okay, so basically we'll choose epsilon to be 1% of 1 over m, and then we're done. So with a choice of epsilon to be 1 over m, our algorithm will be polynomial in n and in the number of samples. Yeah.
For this kind of statement that it's not enough qubits, do you need more qubits than m? M need to be smaller than the number of qubits? Or it doesn't matter? Like if I have only 2 qubits, m is 100.
No, it doesn't matter.
Okay.
Yeah, but you want n to be large.
Okay.
Okay, Zvika, I'm running according to the number that is written here. Is that okay? It's 17 minutes, it says to me. Does this,
Thanks for letting me know. I had no idea this is what it said.
Here. Yeah, no, I'm actually planning to finish in 9 minutes, but I just wanted to.
Excellent.
Okay.
Thank you.
So,
Question, so what's the depth dependence on the
Yeah.
So is there
Exactly. Excellent question. The role of the circuit depth. D needs to be theta of log n. And the reason, the fact that D needs to be theta of log n basically was identified by a recent paper by Deshpande et al. As a sweet spot for scalable quantum supremacy. And the reason for that is because there's a lower bound and an upper bound. Well, let's start from the upper bound, actually. There's a paper, long time paper, an old paper by me and Nikki and Dipagliasso and Nissan, that basically says that after running D layers, so at the end of a depth D quantum circuit, with the probabilistic noise like that, the distribution is within total variation distance 2 to the minus D from completely uniform. So if you want to actually, so either you're satisfied by just guessing the, simulating the quantum circuit by a completely uniform sample, but this is not going to show you any quantum advantage. So if you do want to separate between uniform and this slightly far from uniform distribution, you need at least, by what I said before, you need at least to be sensitive to 1 over 2 to the D total variation distance, which means you need 2 to the D samples. If you need 2 to the D samples, then, and if you want the number of samples to be polynomial, you need D to be at most logarithmic. Okay, so that's the upper bound. From the lower bound, well, a central assumption in the RCS literature is what's called anti-concentration. I'm not going to define it here either, but what it it's defined here, but I'm not going to dwell on it. But the point is basically that the distribution is not concentrated, and this is required for the hardness assumptions. So there are various justifications for why sampling from why the task of random circuit sampling with a statistical test that people have been using is supposed to be hard, and this relies very strongly on anti-concentration. And this anti-concentration turns out that it requires at least log depth to achieve. Okay, so there's a sweet spot of log depth. Okay, so our algorithm at this log depth is going to sit here, we can achieve any arbitrary 1 over poly total variation distance, so we can still distinguish between. So we can mimic whatever test that the test is going to, whatever test that is going to be run, as long as the number of samples is polynomial. Okay, so good. So some remarks. The running time of our algorithm is at most polynomial. It's currently not practical. The reason is that the time it takes is m to the 1 over gamma. Gamma is the error probability, so it has a large exponent. And and previously it was known, not exactly in this way, but Gao and Duan, in a very beautiful paper, basically studied this from motivated by a different thing, and their technique actually implies a quasi-polynomial algorithm, even though at that time they didn't know it because of various reasons that I can talk about later. Okay, so noisy RCS seems, this is very strong evidence. I'll maybe say something about why it's not complete evidence, why it's not an impossibility result, but very strong evidence that noisy RCS cannot be the basis for scalable experimental violation of the external church during thesis. Okay, so yeah.
I remember in the Google paper, they clearly stated that they had complexity arguments that why it would
there is a very large literature on this, and this is a swamp. Okay, this is, I don't want to dive into it. It's I'm also not enough of an expert on this, and also it's really delicate. So the history is in our paper, for example, but I should just say that the evidence apparently is not strong enough. And already in this paper from 2021, very strong doubts have been cast the fact, on those validity of the hardness assumptions. Thomas, do you want to say something about it?
No, I was offering to talk about the gender.
Okay, so, okay, I want to give a glance as to how the proof works, okay? So here it is. This is again the theorem. Mind you, I want to simulate a noisy quantum computer to think of depth, which is logarithmic, to within some total variation distance, which is epsilon. Epsilon is 1 over n, or 1 over polynomial n. Okay, so the first attempt to simulate quantum computers goes by Feynman path integral, and it just requires exponentially many paths. And since there's no reason to think that one path will be more important than the other, you'll have to go through all those paths. And that this is why simulating the straightforward way to simulate quantum computers will take exponentially long. Okay, now the way we go about this is we look at it using a Feynman path integral in the Pauli basis. So what I mean by that is, does this work? No. Yeah, it's there. I can't see this. Okay, maybe you can see it, I can't. Oh, here it is. Okay. Okay. Anyway, it's so I'm looking at this. I'll give up on this. I'm looking at this on the second line, and in the second line, basically you write this probability to get the 0 to the n outcome as something like a Feynman path integral, but instead it's written in operator terminology, density matrices. This is why the double bracket is there. And the identities that you stick in are a sum of all Paulis. So basically, we're looking at a sum over all Pauli paths, where a Pauli path is basically stick a choice of a Pauli on each layer. Okay, so this will be my Pauli path, one particular choice like that. And we call the coefficient that corresponds to one of those Pauli paths a Fourier coefficient in this Pauli basis. Okay, so now here is the basic, the main insight, or which is not by us, it was already done by Gao and Duan. Look at the depolarizing noise and apply epsilon, the depolarizing noise on some operator. Well, it basically takes it to 1 minus gamma A plus some function of the trace of A. In the Pauli basis, all Paulis just go to 0. If you take the trace, they're traceless. So basically, all Paulis are multiplied by 1 minus gamma. And so in the Pauli basis, these Pauli coefficients are multiplied by a factor which depends on the number of non-identity Paulis in the Pauli path. Okay, so there's a decay, exponential decay. And so basically the algorithm is truncate, pick L, the number of non-identity Paulis that we are interested in, to be, say, log 1 over epsilon. And this turns out to give us a sufficiently good total variation distance. I don't want to go into the proof of why this gives sufficiently good estimation, but basically it relies on the fact that because we are averaging over all circuits, it turns out that when you look at the L2 norm of the distance between the two distributions, the cross terms disappear when averaging over the circuits. So you get something which is very classical in a sense. And and once those cross terms disappear, you can use anti-concentration, which we assume to bound this the remaining terms. Okay, so this is not enough because it gives us still quasi-polynomial. In order to actually handle the situation and remove and reduce it to a polynomial, you actually have to look you know, you have to do some work, and you have to go into the combinatorics of these Pauli paths, and it turns out that that not all Pauli paths are valid. In fact, only a very small fraction of them is valid, and we have to be able to run over only those Pauli paths, and I'll skip the details here. Okay, so okay, I also skip the assumptions and leave it maybe to I don't know, to the break maybe, because I want to say something. I promised I want to say. Okay, so it's an exciting time. Concluding this result, I think it's an exciting time to search for a new proposal for scalable experimental violation of the external Turing thesis. Okay, so where can we search? Well, noisy quantum computers is what we have. So let's look at noisy quantum computers. And let's look at them a little bit more closely than we had before. Basically, a noisy quantum computer is something that you start from a noisy state preparation. You let the system evolve without doing anything except for noisy quantum gates. And then you measure with noisy measurements. So that disallows fault-tolerant quantum computation, basically because you don't have fresh qubits. There's no fresh qubits, there's no adaptive measurements. So if this is our model, how can we hope to get, to do some computation in it? Well, in that paper that I mentioned already from '96, we showed that after logarithmically many steps, the distribution is polynomially close to uniform. So we can't go beyond log depth to get anything useful. So, okay, I'll skip this comment. So can we hope for a asymptotic quantum advantage with NISQ devices if this is the situation? Well, this is my last slide, last technical slide. In a very, I think, nice paper that just came out, Chen and Kotler and Huang and Li defined NISQ. And they define NISQ in the following way. They notice that once you do have access to noisy quantum computers of log depth, but you also have classical computers on the side. So NISQ is going to be defined as the class of problems solvable by BPP with access to such noisy quantum circuits without fresh qubits. Okay, so this is NISQ. So what can we say about this class? Turns out that we didn't know that, but we've already for almost 3 years, knew that in fact, this class is very strong. So here are the 2 results that we already know. I'm just reminding you. So first of all, in this system of in noisy quantum computers with no fresh qubits, you can actually run any logarithmic depth quantum computation with, as long as you give up one thing, it's not going to be polynomial size, it's going to be quasi-polynomial size. Okay, so why is that? This is because, well, going back to my paper with Miki from '97 about fault tolerance, this is, as far as I know, this is the only paper that actually showed that fault tolerance can be performed without measurements, without intermediate measurements. It does use fresh qubits. But if the depth is just logarithmic, you can prepare all the fresh qubits in the beginning. And since they only have logarithmically many time steps to decay, you can actually, for every fresh qubit you need at time t, you just prepare polynomially many qubits and you distill them. Even though the distillation is performed by noisy gates, it's still enough. So you can run fault-tolerant quantum computation without fresh qubits, as long as the noise rate is less than some value. Okay, so log depth is in quasi-polynomial NISQ with noise rate which is less than some value. The other theorem, which I reminded you, is that factoring is in BPP with access to log depth circuits. This is another very beautiful paper by Cleve and Watrous. And together, this basically shows that factoring is in NISQ prime, prime stands for quasi-polynomial size, with eta, the noise rate, less than the fault-tolerant threshold for NISQ devices, meaning a threshold without adaptive measurements. Okay, so this is something to I don't know. This is a goal to look up to, and I should just say that in this beautiful paper, they also showed a robustified version of Simon's problem, some variant, in which they actually showed that this variant is a NISC without the prime. Again, where gamma is the noise rate is less than the error rate, than the fault tolerance threshold for NISC devices. So they're also using this result, the fault tolerance without measurements. Okay, so in fact, NISC is very powerful. Thank you. Yeah. So one can actually, so I think, and this is exactly, I want to end with this question. What is the value of the threshold for NISC devices? It's fault tolerance without measurements. And as far as I know, the only place where it was actually estimated is in our paper, from 97, not 99. And there's a question experimentally, is it easier to achieve the NISC threshold, which is small? It's smaller because if you don't have measurements, then it's going to be, it's more stringent, it's smaller. However, it's only for unitary gates. Is it easier than the standard fault tolerance threshold, which has to apply also to adaptive measurements and reset gates? Okay, so the standard threshold requires that the errors are also small for adaptive measurements and reset gates. And the NISC device actually also for reset gates it's required, but not for adaptive measurements and not reset gates during the computation. So, okay, so that's a question. Another question is, I think it's a very, very important question is, could violation of the extended short-termities can be demonstrated in NISC with error above the threshold, meaning without error correction? And I don't know the answer to this. I don't think anybody knows. And maybe such violations can come up from quantum simulations. And really, I want to end with a question, which, again, I want to thank Oded Goldrach and Madhu Sudan for bringing this question, to my mind at least. Have we probed the high complexity regime of quantum mechanics? Thanks.
Thanks, Dorit. We will eat into the break a little bit and take a few questions. Go ahead.
Hi. So for the first question, how would you go about finding the threshold?
Yeah.
Hi. So for the first question, how would you actually go about finding the value of the threshold for NISC devices? Like, what would you need to consider in order to answer that?
There is, okay, so first of all, I'm not saying, our construction is really old and there's been a lot of work since then. But, so you basically want to pick a construction for fault tolerance, and it should work without measurements. And then you have to calculate the threshold for that. So that threshold is one requirement. And the other requirement, which is probably less stringent, is this distillation of input fresh qubits, which is probably, the threshold for that is probably much better, even though you can't use measurements. But it's the same question of calculations of quantum thresholds, but you have to come up with a good design which fits this, which is optimized to the fact that you don't have intermediate measurements.
Sorry, just before the second question, could you potentially take advantage of the fact that you're only targeting log depth circuits when evaluating the threshold? You know, usually the threshold, you want that threshold to apply to polynomial length. Like, does it matter? You don't.
Well, the first thought that comes to mind is that you will take advantage by somehow computing something that sort of foresees the future in some sense, or encodes something along, you know, of several time steps and not just one. I don't have an idea how to do this, but maybe there are new ideas like Fouquet codes and like, I don't know.
Good. Yes, please.
Many of these results depend on whether circuits are local or not.
Of course, I mean, the threshold is going to be the results don't depend on that, but the threshold is going to be extremely different for. No.
Like the log depths there.
No.
Yeah, let's take one from this side.
So there are in the NISQ era some usable algorithms, variational quantum algorithms such as VQE and QUAWA, which are considered in the industry at least to be something that is leading and something that can be considered a path to quantum advantage, but are performing relatively poorly because of noise, because of local minima, etc. Is there a reason to believe that once we reach these noise thresholds that you discuss here for violating ECTT, those variational quantum algorithms will behave better as well and maybe show an ad hoc advantage that is not reached today?
So there are two different questions: the noise, the effective noise, and the question of whether, even if those algorithms are run on an ideal quantum circuit, is there a quantum advantage? As far as I know, there's no proof for the second question of quantum advantage using searching for ground states, etc. I may be wrong. Maybe someone in the audience knows better than that, but even the ideal case is not clear. So the noise. So I mean, of course, if you have fault tolerant VQE, it should perform better than noisy VQE. But even the ideal case is not clear. It's related to the fact that we don't have a way to actually point at a simulation of. It's basically related to quantum simulations of physical systems, and we don't have a way to actually point at a problem that physics does, which is hard.
Fantastic, thank you.
Any additional questions?
Yeah. One question. Why you said that we don't allow intermediate measurement? Why can't we, in any case, just delay all measurements to the end of the computation, like you standard?
Well, you could, but the problem is that this will incur an exponential overhead, because this principle of delayed measurements basically relies on the fact that you have additional ancillas to copy your state to, and then and that's qubit that you're copying to needs to be to have some information in it. If it's completely mixed, as it would be if it just waited there for the whole computation until you copied it, then you're in trouble. If that qubit is completely is close to mixed, then copying to it doesn't mean anything.
Thank you.
Yeah, I think this self-moderation thing is working pretty well. So if you want to ask a question, just go ahead and do it.
Hi, I just want to ask, is factoring the only thing that we can hope to show quantum advantage with? Are there other well-defined problems that?
No, there are many questions that you can show advantage for. Many problems that we can hope to show advantage for, meaning all the quantum algorithms with exponential speed up, claimed exponential speed up, they're not so many, but more than just Shor and Simon's problem. But this shows actually that this was actually focusing on whether we can show advantage in the NISQ era without fault tolerance. So far, as far as I know, these are the only two examples that are candidates for showing asymptotic advantage in the NISQ era, which is really thought to be, which is really a valid suggestion for a problem, which is computationally hard for classical computers.
Yeah, there are two problems being factoring, and what's the other thing?
I'm sorry?
You said.
Oh, the other thing is Simon's, the robustified Simon's problem that Chen et al. proved.
Hi. I wonder if we shouldn't just exercise patience in some sense. Like, first of all, do we agree that if we have Shor's, if we can run Shor's algorithm, then everything is resolved, right? Would you consider that's fine, right? Yeah.
I don't know. I mean, I would be very satisfied.
Yeah. Right. So I wonder if some of these would be relevant. So I think that we can wait for, I don't know, 5-10 years, and then we'll all be happy. And I wonder if some of these lessons are relevant even after scalable quantum computers would exist. And this would be, I view this as you know, a more fundamental question, even after fault tolerance computation exists. So what are your thoughts about this?
So about the second thing, I don't know. It's kind of the connection that I made here is basically the connection of preparing fresh qubits. So I don't have much to say about the second question. About the patients, well, I put this slide twice, this picture. And I have to say that, first of all, I think that all of what I said basically points to the fact that even though, so it basically points to the fact that the error rate is even more important than what we thought earlier, I think. We are finding it hard to go below the error rate that is required for fault tolerance. And I don't know, maybe there is a reason for that. I'm not saying that there is a reason for that, but we haven't crossed that threshold. Okay.
Thanks. So just seconds. So, I mean, it's a very great result and discussion, but we should give ourselves a little bit of time for the break. So if there's a burning last question, then jump and ask it, and then we'll take a break.
I think coffee beats.
I put the bar pretty high, but okay. So let's thank Dorit again. And we'll come back from coffee at 1/4 past the hour.